Our next speaker, David Abel, is a senior research scientist at DeepMind in London. His research focuses on bringing clarity to the central philosophical questions surrounding agency, computation, and learning. And today he's going to talk about the reward hypothesis. Let's welcome David.
I first want to thank all the organizers. It's been a really fun event so far. I've just been taking a lot of inspiration from the earlier talks and lots of questions I want to think about. I'd love to discuss more with you all soon. This is a clicker, perfect. Okay, so I'm going to talk to you about the reward hypothesis. This is joint with a bunch of collaborators across a bunch of institutions. We've been doing this work over a number of years, started back in 2020. The motivation for this work really stems from the need for definitions. So a lot of my recent work has been unified under the theme of trying to provide definitions that I think provide a lot of clarity and a cleanliness and tidiness to kind of the foundations of the field. So I love this quote from Will Quine, who says, "The less a science is advanced, the more its terminology rests on an uncritical assumption of mutual understanding." This really speaks to the state that a lot of kind of younger scientific fields find themselves in, where they're still sorting through the paradigm. They're still figuring out what are the central definitions, models, tools, and so on that the field just sort of organize around. And of course, within AI, we have this big definition of intelligence that people have been debating since maybe the field's founding in the 1950s. But similarly, I think things like the definition of an agent, or perhaps the definition of learning and the definition of goals or tasks are still sort of up for debate. And I'm really excited about this workshop as a space to think carefully about what could we mean by goal, what could we mean by task, what are the pros and cons of adopting different perspectives on what we mean by these different concepts. And so a lot of my recent work has been trying to dig into this question about what is a definition of an agent and a goal. And my preferred definition of agent comes from this Richens and Everett paper and this earlier book by Dan Dennett, which says agents are goal-directed adaptive systems. But this partially kicks the can down the road and says, gosh, we first need a definition of goal-directedness in order to really get our hands on a clean definition of agent. So that's where we find ourselves today. How can we first cleanly think about the question, what are goals? What are the possible options of how we can understand what a goal or a task is? And one proposal comes from Rich Sutton, which is the reward hypothesis, which says roughly that we can think about goals or purposes in terms of the maximization of reward. Now, this hypothesis, I tend to think about it, and when we're thinking about specifying a task for a robot, we imagine a task designer, Alice, that has some space of possible goals she has in mind that she'd like a robot to pursue. That Alice can write down a reward function in some form, some representation, that can produce signal for some learning system that can, given access to that signal throughout the robot's experience, can eventually come up with a solution to that task. That's how I tend to think about what the reward hypothesis is saying. No matter what goal Alice starts with, Bob can eventually solve that goal. Now, roughly this means what we're going to study when we study the reward hypothesis is just this simple statement. Can all goals be written down in terms of a reward signal to be maximized, yes or no? And that's roughly the goal of this work. We want to treat this as a genuine scientific hypothesis. We want to ask, can we somehow falsify this hypothesis? Can we find supporting evidence for it? What are the conditions under which it holds? What are the limitations of reward? And the main result we're going to build to in this talk is to identify some precise conditions that tell us exactly when the hypothesis is true. And if it were sort of unambiguously true, then there wouldn't be any conditions. And so I'll just say right now, the hypothesis is false in a certain sense. There are some weird edge cases in which the hypothesis fails to hold. But what I found as I've kind of been working on this and talking to folks about this work is that often these edge cases are the ones where we say, well, those aren't really interesting anyway, are they? And so it's kind of up to us to interpret whether or not we think that these edge cases are meaningful or not. I happen to think they are quite meaningful. Okay, so the way we're going to, yeah, can you hear me in the mic? That sounds good. Okay, perfect. So the way we're going to organize this result is in terms of a number of doors that you're allowed to walk through if you want to reject the hypothesis. And these will roughly be the assumptions that we can make that can get us away from having to accept that the reward hypothesis is true. So we'll reveal a few different doors of two kinds. The first set of doors are ways of interpreting what the hypothesis means. I think there's a lot of room for interpretation in this original kind of natural language statement, the hypothesis, and that's what these first two doors will give us. The second set of doors will then evaluate the hypothesis, given that we've already made a commitment about how to interpret the hypothesis. And so you can kind of decide for yourself which of these doors you might want to walk through as a way to reject the hypothesis. And then if you don't walk through any, you kind of have to accept that the hypothesis is true. Okay, so let's get some notation on the board in order to make some of these claims a little bit more precise. This is going to be a particular flavor of reinforcement learning, largely inspired by this line of work on general RL from Marcus Hutter and colleagues, as well as recent work from Ben Van Rooij's group. So we start from an interface, which is a set of actions A and a set of observations O. These give us a set of histories. These are just sequences of action observation pairs of arbitrary length. This will give us an environment, which is a function from any length history and the agent's latest action to a distribution over observations. And then a policy is going to be a history-based function that for each history assigns a distribution over actions. So this is going to capture something like the reinforcement learning problem, but so far we haven't mentioned rewards or goals at all. We just have these two history-based functions exchanging action signals and observation signals back and forth. Okay, so our rewards are going to be captured by these Markov functions. So they'll just take the last action and observation. We'll talk about history-based rewards a little bit throughout the talk, but we'll be most interested in Markov rewards and asking about their expressive power. We'll also introduce a action and observation condition discount. This is proposed by Martha White, this really cool paper on task specification. And we'll adopt that convention, which will give us additional flexibility for grounding goals into rewards. That will give us a specific notion of a value function. I just write this out because we're going to need this as part of our efforts to interpret the hypothesis more precisely. So this is our traditional notion of value. It's expected cumulative discounted reward. But notice that we have this product over discounts as well, since the discount now depends on the action observation pair. And as a special case, of course, we can assign a constant to all actions and observations, and we recover traditional value. Okay, so that's basically it for notation. We'll come back to the pieces that we need later on. But for now, let's look at the first two doors, which are ways to interpret what the hypothesis could mean. So what we're going to get at the end of this is a conjecture that we think captures the spirit of what the reward hypothesis is proposing. So recall, this is the hypothesis. And our first door is going to really ask, what exactly could we mean by goals and purposes, if not reward? I've heard Rich say, we can think about reward as the atomic unit of what a goal is. And if we're asking about whether rewards can capture goals, we need some other language to talk about goals, like perhaps forms of temporal logic. We're going to adopt the perspective of thinking about preferences in their most general form as a notion of goal or purpose. So any preference relation over outcomes is a form of goal or purpose. I think this is sort of a separate hypothesis we're proposing in the background that we need to get this work off the ground. Would love to talk about that more, because I think there's a genuine question to be had of whether this is a sufficiently expressive language as well to think about goals. But what that means is we'll start with some set of outcomes. So a classical example is to say, I prefer, say, an orange to an apple. We'll use this little greater than symbol to indicate that, and we'll refer to this as the preference relation. We can, of course, extend this to things like Carrot Bandits, where you might have a selection of options, and then you prefer, say, the pie to the sandwich. We can use the same preference relation in things like chess, where you prefer one state to another, perhaps where your side of the board is in an advantageous position. And we can generalize this to the history-based case, where you just say you prefer one history to another. So our most general form of preferences is going to be preference over arbitrary histories. So that's the first door. The second door is really digging into this part of the hypothesis that says well thought of. So what would it mean for a goal or purpose, in our case, a preference relation, to be well thought of in terms of the maximization of reward? And for us, what that's going to mean is that the preferences can be captured by rewards in some way. So this part will need a little bit more detail to get into, but that's the high-level picture. Can we somehow communicate a preference relation with an arbitrary reward function and discount? So the way we make this more precise is by saying, for any choice of a preference relation, there will always exist a pair for reward function and discount that captures the preference relation. And what we mean when we say it captures the preference relation is that there will be an equivalence between our preferences over policies, those history-based functions, and the values that we assign to those policies. So if this relationship holds, then we will say that the general statement holds. So we're getting pretty close to a conjecture. At some point, we'll just replace this for all and there exists with actual quantifiers over these sets, and that will give us the more formal statement. I'll need to say a little bit more about these policy preferences and values, but the details are roughly what you'd expect. We'll start by talking about these policy values. These are going to be n-step policy values, and we'll have a little bit more to say about n in a moment. But policy preference are sort of funny objects, so let's make that a little bit more precise. Really what we mean by a policy preference is a preference over the outcomes produced by those policies. So for any given two policies, we can think about the distribution of outcomes generated by those policies. And that can be captured at a particular length history, n, by this quantity dn pi. So this is just with what probability will this policy and this environment produce this history of length n in this environment. So that allows us to think about the outcomes of a particular length. In order to get the more general notion of policy outcomes, we can talk about the preference between outcomes at a particular point in time, and we'll generalize this in a moment. So what we will mean when we talk about this coherence is that the value at length n is equivalent to our outcomes of the distribution of our outcomes of length n. The final little nuance, there's a few little subtleties along the way, is that we need to be able to talk about all n larger than some n. And so what this roughly tells us is that the preferences are kind of finitely we can evaluate them in finite time. There is some n where we don't need to look past it in order to determine whether we prefer one policy to another. And I was thinking during Hadassah's talk whether how our results will relate to linear temporal logic. And my thinking was this might be the departure point, that temporal logic will go beyond what we do here. So to make this more precise, we'll say there must exist some point in time such that forever after, the policy outcomes, our preferences, and the values agree with each other. That means they're allowed to switch before that finite point in time. So for instance, you could like how the orange hiker reaches a particular destination, but you could like where the purple hiker gets to in the end, as long as eventually you prefer one to the other. And this gets away from a lot of really peculiar cases of preference relations, for instance, where you prefer odd length histories to even length histories. There's all sorts of weird cases that this gets us away from. Okay, so now we're just about to the formal conjecture. We say for every preference relation, there must exist a reward function discount pair such that this relation holds. Our policy outcomes are agreed with by the way we assign value for all n greater than n. So that gives us this following conjecture. And again, these two quantities are just the outcomes and the value. So those are the first two doors. You might disagree with how we've chosen to interpret the hypothesis, but we suggest this is at least one natural way to ground out some of the details of the hypothesis to study it in more detail. So the next step is now to prove whether this hypothesis is true or false. That's going to be the second set of doors. But you might already have decided, you might have walked through one of those first doors and just disagree with how we're choosing to interpret the hypothesis. Okay, so now for the second set of doors, we can see right away that this conjecture, as stated, is false, because the way the conjecture starts is far too general. It's for every preference relation. But so far, we haven't really done anything to rule out peculiar preference relations aside from get rid of those that finite evaluation condition. And so, for instance, we could imagine an intransitive preference relation. You might prefer oranges to apples, apples to grapes, and grapes to oranges. There's nothing to stop us from writing down that preference relation so far. And so this little counterexample is sort of hinting at some of the conditions we're going to need in order to close the loop on this conjecture. But in its most general form, we'll see that there are a variety of counterexamples that make this conjecture false. So what we'll need are a set of constraints on the preference relations such that we can recover a reward function and a discount pair. And those constraints are going to be the next 5 doors. You can choose to accept those constraints or decide, gosh, I don't want to violate those constraints. I'd rather walk through one of these doors. Okay, so the 5 constraints are going to be roughly the classic von Neumann-Morgenstern axioms from expected utility theory, kind of adopted over to this history-based RL framework. So these come in the form of 4 axioms, and then we'll have a 5th at the end that I'll mention briefly. The first axiom we call the completeness axiom, which says that your preference relation has a genuine preference over every possible outcome. You can't abstain in any case. The second axiom is transitivity. So this rules out the case we just mentioned in terms of preferring these, this little circle of fruits. The third axiom is called independence. And roughly this means you can't mix together independent alternatives and somehow invert your preferences. We'll go into a little bit more detail on this one as well, because I think this is a particularly important one for us to reconsider in task specification, because this one will actually get rid of risk-sensitive objectives and things like constrained objectives. The fourth is called continuity, which just means there's always a way to break even between any 2 outcomes. And together, these 4 axioms comprise what are called the von Neumann and Morgenstern axioms, proposed by von Neumann and Morgenstern, and it's kind of a landmark book, also from the 40s. And this closed a much earlier hypothesis called the expected utility hypothesis, proposed by Bernoulli in the 1700s. So these collectively tell us that maximizing expected utility is sort of the right thing to do if you satisfy these axioms, and these together will motivate history-based rewards. But we were particularly curious about Markov rewards, and it turns out in order to recover Markov rewards as the kind of correct thing, we need a 5th axiom, which we call temporal gamma indifference, which says roughly that the way you're discounting is consistent throughout time. There's more to say about that too. So I'll just give you a quick flavor of some of these axioms and kind of their basic structure to get a feel for what kinds of preferences they rule out. So we'll start with completeness. So this means you have a genuine preference between every outcome. So for instance, if you look at this tree of all possible histories, every point on that history tree, you have to have a preference between these 2 points. And in this sense, it's, I think, the most fraught axiom in many ways. Historically, there's quite a lot of work that argues against completeness, in part because the preference relation has to have an answer for kind of an infinite space of possibilities. So there's this really great paper by Aumann in the 60s that tries to reconstruct utility theory without the completeness axiom to some degree of success. And there's some kind of more philosophical arguments against the use of something like completeness that lean on these notions of incomparability or incommensurability, right? So in this paper, the author suggests, how can we compare violations of different virtues, like being honest as opposed to being just? These are just not 2 things that you can exchange between. Or similarly, how can you compare, eating an orange with a walk on the beach? They're just not comparable in any sense. And so there are just some experiences we shouldn't expect people to be able to trade off between. So the third axiom, independence, I mentioned that this throws away things like risk. The reason for that is if we have a preference, what this axiom means is if we have a preference over to an orange over an apple, it has to imply that if I give you a chance at getting an orange and the same chance of getting an apple, you have to prefer the chance of the orange. So the chance of getting something can't really change your preferences. And this is why risk-sensitive objectives are thrown out by the third axiom. So if we want to specify tasks that take into account riskiness or uncertainty, then we need to get rid of this third axiom. Okay, so with those 5 axioms, we can now state our main result, which is just that the conjecture I mentioned before is true, if and only if those 5 axioms are satisfied. So I want to highlight this if and only if, because this means anytime we write down a reward function, we're implicitly talking about a preference relation that satisfies the 5 axioms. So this is a huge requirement to place on the kinds of reward functions that we write down. Maybe intransitivity is an easy one to avoid, but I'd claim that some of these others, things like independence, are probably a little bit harder to ensure that we're capturing in the right way. So as I think about the space of RLHF right now and the fact that we're continuing to form reward models based on preference data, I think it's very likely that oftentimes the preference data we're collecting, these preference relations don't always satisfy these 5 axioms, which means we're assuming that the noise in the data should, or that any deviations from these axioms in the data should just be treated as noise. And that feels wrong. It feels like we're doing something wrong there. So this is the main result. Here are the 7 doors. The first 2 I mentioned are, how do we interpret the hypothesis? What does this hypothesis actually mean? And then these 5 axioms comprise the set of constraints on preferences we need in order for reward to sort of be the right thing to do in order to capture the goals that we care about. So I'll just highlight a few takeaways that I think are probably particularly important for thinking about task specification. So the first is, in a particular sense, the reward hypothesis is false. At the very least, there's nuance. So at the very least, there are choices of preference relations that we just can't write down in terms of a scalar reward function. Whether this means we should be thinking about multi-criteria objectives or deviations from the expectation, kind of up to us, whether or not these are actual limitations or not, but I think it's an important thing to highlight. So what this means is that there are choices of these goals that we cannot capture with a reward function in discount pair. So the second takeaway is that, as I mentioned, kind of people tend to not satisfy these axioms. So there's this really, I think, brilliant line of work from Kahneman and Tversky and Johnson and Laird in behavioral economics that shows people regularly deviate from the norms of rationality, which means, okay, thank you. Which means that if we're thinking about writing down reward functions based on our preferences, we need to be aware that our preferences don't necessarily satisfy these norms. As one example, if you're asked to choose your favorite shirt from amongst a collection and you're given a really big pool, Kahneman and Tversky had this nice experiment where they showed if you then ask the same participants to choose from a smaller pool, oftentimes preferences will invert. You'll end up preferring one shirt to another that you didn't when it was a bigger set of options. And this just speaks to the kind of complexity of human preferences, and that I think it really goes far beyond these traditional axioms of decision theory. So when we think about these 5 axioms, I think there's probably good reason to think that at the very least at the population level, we deviate from all 5 of these all the time. And so what I think that means is that when we write down reward functions, as I mentioned, we're kind of assuming that the preferences are rational, but really there's this space of, quote unquote, human preferences that maybe only have minimal surface area with this space of rational preferences. And as a result, I think it's probably important that when we specify tasks, we really kind of think more about the human at the center rather than the decision theory at the center. And we kind of make sure that we're incorporating the ways that humans prefer things and think about tasks into the way we write down our objectives. The third takeaway is that the deviation from independence in particular, I just want to emphasize again, I think this is one of the biggest opportunities for task specification, to think more about uncertainty, to think more about risk, to think about multi-criteria or constrained objectives. This feels like a big opportunity to really expand what's possible out there right now, to design algorithms for specifying these and learning algorithms and planning algorithms to account for these kinds of objectives. In the appendix of one of the papers I'll mention, we have an algorithm that is guaranteed to return the satisfying reward and discount pair, given this preference relation as input. The caveat is you need this preference relation to satisfy the 5 axioms, but this is actually an efficient algorithm to produce this reward discount pair. It's not really something that we can run right now because we have to assume the preference relation satisfies these axioms, but it's an area I'm again excited about maybe basing approximations off of this algorithm. So the work I presented today is based really on a line of 2 papers. The first was from 2021, and then last year, this paper led by Mike Bowling and John Martin, and joint with Will Dabney, called Settling the Reward Hypothesis. This is really where most of the results I mentioned come from. So if you're curious, I encourage you to check out those papers. I want to extend a huge thank you to all my collaborators that have been involved with both of these projects. Really enjoyed working with everyone. It was a really fun group. And with that, I will close. Thank you so much.
Yeah, that was awesome. I'm still a little bit on the independence side. So, what do you mean by that? Let me ask this. So, should I, regardless of the probability of orange versus apple, I should always pick orange, and if the probability that was smaller, or what is it? What is it?
Right. Yeah. Good question. Yeah. Thank you. So the version of it that I like the most is that if you have the deterministic outcome, so you just are choosing between an orange and an apple, by telling me which of those you prefer, it also tells me how you prefer a chance of getting each of those things when the chance is the same. So if I give you a weighted coin and you tell me you like apples, or sorry, oranges more than apples, and then I give you a coin of any weight, you have to prefer the chance of getting the orange versus the chance of getting the apple. So the chance can't suddenly invert your preference, say, well, if there's a chance I won't get my orange, then I want my apple instead, right? That's the key. Yeah, thanks, Anas.
Discount factor, because you had correlation,
Yeah,
and I wonder how much of it's played now, because focus a lot about the rewards and people that do machine learning usually focus about learning the reward, but is the discount factor is like a very crucial part here?
yeah, good question.
Is it very simple or like satisfied that you can only do things about
Great question. And let me just make sure I remember to repeat for the folks online. So the question is, I focused a lot on the rewards. Does the discount factor matter as much? How does it play out? Yeah, great question. Thank you. So I'll say that we adopted this perspective of discounts that depend on action and observation as a way to generalize from the traditional framing. So if you choose a constant discount factor, it could even be one, you could use average rewards, for instance, then that's a special case of this choice of discount factor. So we just wanted to make sure that if you do something else with your discount factor, as Martha White proposed in this earlier paper, that we can also account for how that plays out in the reward hypothesis. So it might be for some choices of preference relations, there are only kind of action observation conditional discount factors. You can't get away with a constant. So it does enrich the expressive power by moving to actions and observations. And we just want to make sure we're accounting for that as well.
So I agree, and I understand what you did, but just out of your experience, you have the algorithm to generate the reward and the discount factor. Does it usually is something natural, or it could be that I will get something very weird?
Yeah, good question. So
the theorem will be met, but only because I allow this weird function to do something weird, and it's not the action that reward.
yeah, interesting. I think the discounts probably are weird in some cases. Depends on how we want to think about weird, but typically we'll start with a utility function, and then you sort of unwrap what the stepwise rewards need to be. And then that points to what the discount factor has to be as well, in order for the utility function to capture your preferences. So could be weird in some cases. That's how I summarize. Yeah, happy to talk more though. Thanks.
Say something quick, which is, this is a great talk, I really enjoyed it.
Thank you.
But you missed an opportunity
Mhm.
because you're in the Netherlands.
Okay.
You didn't say anything about Dutch book. Dutch
Oh.
book there.
Yeah. Good point. Yeah. Yeah, so Dutch booking is about an adversary kind of taking advantage of how you've chosen to prefer things, basically. Great point. If I get another chance, I will include a slide. Thank you.